Hello class, welcome to the lecture on attestation protocols and trusted computing. We are starting a new module. The module is on cloud computing, and although attestation protocols are being covered as part of this unit, it is important to understand that attestation protocols and trusted computing, even though they play a very important part in cloud computing, have applications beyond cloud computing as well. Okay. Nevertheless, because they are such a fundamental part of cloud computing, I decided to cover this topic under the umbrella of cloud computing and cloud security. So let us get started. Um, Let me see how to hide this thing over here. Okay, I hope it goes away over time. Um, yes, it does. All right. So here is the problem that we are going to be addressing today. The question that we're going to ask ourselves is, how does one attest the software stack that is running on a remote machine? So here's the setup. Maybe there is a remote machine. Okay, maybe this is a machine that is sitting on the cloud somewhere or some remote server. And this remote machine is making some claims about what software it's running, right? It's saying, look, for example, just to take a hypothetical example, and all of these uh, version numbers over here are made up, but anyway, you get the idea. It's saying, look, I'm running a Windows 10 operating system. The patch level is 1729. Okay, so that tells you exactly what code this remote machine is running, and the applications that I'm running are, as far as you are concerned, I'm running the Apache web server version 2.5, and I'm running the MySQL database server version 4.7. Okay, as I said, these version numbers are made up. These might not even be valid version numbers. I don't even know what the version numbers are, but you get the idea, right? Basically, the idea is that the remote machine is saying, look, this is precisely the software that I'm running. Now you're sitting at your end, you're the client of, let's say, this remote machine. And when the remote machine makes this claim, right, you want to be able to verify this claim, right? Um, because perhaps you're paying for the service that this remote machine is offering, and you want to make sure that you're getting what you paid for. Okay. So the question that attestation protocols and trusted computing attempt to address is precisely this, where you are able to verify claims made by the remote machine about the software stack that is running on that remote machine. Okay, so that's precisely what attestation protocols are. They are a set of messages that are exchanged between the remote machine and your machine in this picture, that allow the remote machine to prove to you the integrity of the software stack that is running on the remote machine. So because of the setup that we just described, you are often called the verifier, because you will be verifying certain claims made by the remote machine. And the remote machine is going to be called the prover, right? The prover is the one that is trying to prove certain claims about what software they're running, and you will be verifying those claims. If you successfully verify those claims, you have reason to believe that the remote machine is telling the truth. And if the remote machine is lying, you'll be able to catch it. Okay, so that's the idea behind attestation protocols. So we are going to be studying attestation protocols in a fair amount of detail, and we will see attestation protocols being applied in a couple of other lectures in the remainder of the semester. Okay, so before we delve into attestation protocols and the details of how these attestation protocols work, let us understand some motivating applications. Okay, so there are many very useful applications of attestation. We will look at 4 applications. So the first application is something that I already mentioned. In cloud computing, for example, a cloud client may wish to ensure that the cloud provider is indeed executing the software stack that the cloud provider promised as part of the service level agreement with the client. Okay, so the client actually wishes to verify that the cloud provider is telling the truth so that they are getting their money's worth. Okay, so that is something that is going to be possible as a result of performing the client performing an attestation of the cloud server. There's a second application that is very closely related to cloud computing, which is that of remote billing. Okay, so let us suppose that to follow the model of cloud computing, a server that is providing some services to clients charges the clients based upon the resources that the client's code consumes on the server. Okay, so the resources may be things like memory, they may be things like storage, uh, CPU utilization, whatever it is. Okay, so the server charges the client based upon what the client is consuming at the server's end. So this is identical to the model of cloud computing today. And at the end of the month, perhaps the server produces a bill to the client saying, this is what you owe me because you consumed all of these resources on my end. The question to you is, how does the client trust that the bill is correct? Right? How does the client actually verify the bill? So one way that the client can actually verify the bill is that you get a breakdown of the costs from the server saying, look, if you consume this much memory, you're going to be charged so much. If you consume so much CPU, you're going to be charged so much, and so on. And the client could run its computation locally and ensure and actually measure the computation as it's running to ensure how much CPU utilization is there, how much memory it used, and so on, and then check the bill based upon the server's breakdown. Whatever the server's rates are given to the client. Server runs it, the client runs it locally, and then matches the bill. Okay, so if the bill matches whatever the server gives, great, the server is telling the truth. But what is the problem with this solution? So the problem with the solution is that the client is having to run all of the code locally. And in doing so, you have defeated the purpose of cloud computing, which is to outsource all of your computation to the cloud. Okay. So this is a non-starter, therefore, this particular solution of replicated execution. Not just that, the client may not even have actually the hardware resources to run to run this computation. The client may not even have exactly the same hardware configuration as the cloud server. That is one of the reasons you go to the cloud, right? Because you cannot afford to buy that hardware. That you can rent it for cheap, but you cannot actually afford to procure it locally. So it might not even work, even if you want it to work. So another solution is, of course, replicated execution. The client takes their code to two different cloud providers that are mutually distrusting, that you assume don't collude in some way, and you run it on both cloud providers, and each one has their own billing rate. But at the end of the day, you apply each one's billing rate, and then you try to correlate between the two the two bills that you receive, and then try to make sense whether both of them are correct. So what's the problem with this solution? Well, the problem is that you're paying twice the amount, right? You're paying the first cloud provider and you're paying the second cloud provider. So again, it's a very expensive solution to a rather simple problem. Okay, so instead, here is a third solution that I'm going to offer, the one that's listed on the slide, that will be enabled by trusted computing. Okay, so supposing that the client and the server together agree on the billing software that the server is going to use. Okay, so the client has the chance to actually inspect the billing code. The billing code hard codes all of the rates. It contains all of the measurement probes that the server will use. So, for example, to measure the amount of memory used, the CPU utilization, the storage, and so on. So, this particular billing software is agreed upon by the client and the server. Never mind where exactly the billing software will run on the server. It will actually have to be downloaded within the hypervisor or the operating system, and it can be done so as a device driver or a kernel module. Nevertheless, the idea is that this is some software that is going to be doing the accounting on the server side of the client's code that's running there. So the client and the server because they have agreed upon this in an act of mutual agreement, saying this is going to be the billing software. But implicitly, by the way that we have set things up, the client therefore trusts the output of the billing software. Okay, because the client has okayed the billing software, and the server is just going to run it. So all that the client needs to do in this case is to verify that the server is running that billing software. If the client can verify that the server is running that agreed upon billing software, then the client can trust whatever the billing software output is, right? And therefore um, it can believe the output of the billing software, and it will know that the server is not lying. Okay. So in order to accomplish this, the client can ask the server to attest its software stack and ensure that the billing software is running. So this is yet another application of attestation protocols. So the third application is that of malware detection, or rather proving the absence of malware. Again, we can talk about this in a cloud setting, you know. So the client may wish to ensure that the server is only running some known good software stack as part of the configuration that it's providing. And for example, a cloud provider may wish to install some malicious software in their hypervisor or the container software um, that peeks into what the client is doing and record the state of the client's computation and then monetize it later on, right? So the cloud provider in this particular case is compromising the confidentiality of the client's computations. Or the cloud provider may actually inject data, corrupt things, and so on. And the client might actually want to get an assurance that the cloud provider is not up to these kinds of activities. So the client may wish to ensure that the server's code, the software stack, the infrastructure that's on the server's end is free of malicious software, including rootkits, by the way, malicious software that's running inside the hypervisor or within the operating system. Okay, so the simple solution here is that if the client actually detects some malicious software running on the server, the client can refuse to give its business. It can say, look, unless you run this particular set uh, of uh, uh, of software as part of your software stack, and you run only these things that I trust, this known good software configuration, I'm not going to give you my business. Okay. Again, over here, this is a problem for attestation. The client can request an attestation of the server software stack, and it can study the attestation report, which is basically the proof that the server gives to the client, and ensure that the software that's running on the server uh, is only the software that the client trusts. Okay, and therefore you can prove the absence of malware, or rather show that or establish trust that only software that you are okay with is running over there. All right. So while these first three applications that we spoke about are in the domain of cloud computing, there is a fourth one that is in the domain of mobile devices, and the uh, the solution that we are going to talk about applies in the enterprise domain, where there's an increasing trend in companies and enterprises to allow employees to bring their own devices. Okay, so the idea is the companies want to save some money. They don't want to, equip their office with thousands of laptops and desktops. Instead, what they say is, look, dear employee, bring your own phone and laptop to work. You are comfortable with your own device, and we will give you a virtual machine setup for your work. When you're here, just log into that virtual machine. You run that virtual machine on your own device, and you can accomplish all of your work. The hardware belongs to the employee. So, imagine the cost savings to a company if they can do this. All they have to do is provide the corresponding virtual machines, and everything is done. So this particular trend is called BYOD, or bring your own device. Um, The only problem here is, of course, how can the enterprise ensure that the employee's device is free of software that may, for example, snoop into the enterprise work environment. Okay, so the employee may be malicious. They may have some sort of malware that's installed on their machine that is going to look into the state of this virtual machine and steal the corporate secrets. Okay, which can include the company's code, the company's internal documents, trade secrets, and so on. Okay, so this particular setting you can see is that it is extremely relevant to the times that we live in, right? It's relevant for remote work, or what is also called work from home nowadays. So even here, the solution would be that the company server will seek an attestation report from the employee's personal device and only allow personal devices that have a software stack that is acceptable to the company. Otherwise, the employee is forbidden from using their own personal devices uh, for work. Okay, so that particular device will not be allowed to uh, download the virtual machine for the work environment. Okay, so yet another application of trusted computing or attestation protocols. Okay, so I gave you 4 applications of attestation protocols. Now, in order for all of this to be possible to accomplish these goals, the client, in other words, the verifier, needs to have some root of trust on this remote machine. Okay, so I will make clear what this root of trust is shortly, but the idea is that there needs to be some basis of trust, because otherwise, if you don't have any basis of trust, this remote server, let's say, the remote server just makes this claim: okay, I'm running Windows 10 patch level 1729, blah blah blah. You can just believe it, right? But will you believe everything this remote machine is saying? No, because the remote machine can just lie, right? So if you have to be able to trust this, you need to have some basis over here on the remote machine, something, some sort of hook that allows you to establish some trust into what the remote machine is saying. All right. So we will call that basis, that hook, a root of trust. So failing the existence of such a root of trust, such attestation protocols are not possible. Okay, so we are going to assume some roots of trust, and in fact, that root of trust uh, is actually a piece of hardware, and this is a very special kind of hardware. It's called trusted hardware. Okay, and in fact, this trusted hardware comes in many forms nowadays. I'm going to be listing 3 over here that we are going to be studying as part of this course. So the first one, which we are going to be studying in today's lecture, is called the TPM, or the Trusted Platform Module. So this was developed in the early 2000s, standards for the TPM, and it's the first widely deployed commercial trusted hardware mechanism. Okay, your laptop likely has got a TPM. If you check your device drivers, uh, you will actually see the device driver for the TPM running on your machine. Okay, so we will be studying the TPM today, as well as attestation protocols based on the TPM. Now, there are other forms of trusted hardware, in particular the SGX and the ARM Trust Zone. Okay, uh, but these pieces of hardware, SGX and ARM Trust Zone, in fact, offer much more than attestation protocols. The TPM offers just attestation, nothing else. Okay, SGX and ARM Trust Zone offer much more. But attestation is a very important part of both SGX as well as ARM Trust Zone's working model. So in this class, we will be studying SGX. In fact, we'll be studying it in the very next lecture. and ARM trust zone when we look at mobile devices. So in both SGX as well as ARM trust zone, I will be referring to attestation protocols, but not talking about them in detail. But the attestation protocols that I'm going to be talking about over there are going to be identical to the attestation protocols that I will be talking about in today's lecture. The only difference will come from, where certain encryption keys are stored, uh, and how the encryption happens and so on. But other than that, it's going to be identical. Okay. So let me briefly tell you about the other two as well. So SGX is a piece of hardware from Intel. It stands for Software Guard Extensions, and it allows encrypted execution in the cloud. Uh, Next two classes after today, we'll be studying SGX. The first time you look at it, it looks like magic. Uh, but we'll be understanding SGX in a lot of detail. Um, okay. And of course, the third piece of trusted hardware we'll be studying is ARM Trust Zone, or we'll be looking at one application of ARM Trust Zone. So ARM Trust Zone is available on pretty much all mobile devices today. Your uh, mobile phone likely has ARM Trust Zone running on it. If you have ever heard of Samsung Knox, which is a very popular solution on Samsung devices in enterprise settings, ARM Trust Zone is the basis of Samsung Knox. And it ARM Trust Zone also serves as the basis for protecting the state of many mobile payment applications. Okay, so for example, your payment information and so on, the way that these things are protected on these mobile devices by ARM Trust Zone. So it's likely running in your phone as well. SGX is less well deployed, at least on client devices. It is popular on the server side. Again, we will study it next two classes, and I'll tell you about what the challenges with SGX are. But today we'll focus on TPM, or Trusted Platform Module, because it's the simplest hardware that you can study, and it does pretty much one thing, which is attestation, and does it well. Of course, there are shortcomings in the way that TPM does attestation as well, but all of those things will become clear over the course of this lecture. Okay, so the TPM, as I said, was proposed in the early 2000s, and nowadays it's available in most modern chipsets, be it desktops or laptops, and it costs pretty much around $5 or so. So extremely low cost. That is why it is so widely deployed. Okay, so the TPM provides this basis of trust, or the root of trust, on the machine that you want to attest. Okay, and it forms the basis for all attestation protocols. So the full specification of the TPM was developed by the TCG, or the Trusted Computing Group, and it has a lot of detail. In fact, this is why the assigned reading for this course uh, contains TCG right in the title. It is the design and implementation of a TCG based attestation protocol. Um, they are talking about the Trusted Computing Group. In fact, they are referring to the TPM, but that's how they title their paper. And the TCG's full specification of what a TPM should look like is a rather detailed document. And we are not really going to look at all of those details. Uh, we are only going to be looking at some core ideas of the TPM. And in fact, only one of the applications of trusted computing, namely a technology called trusted boot or secure boot. Uh, and we are going to be abstracting away from all of the low level details of the TPM. Although if you were to actually do a project and you know uh, uh, implement something with the TPM, you'll have to understand all of those details uh, at a rather low level. But we are not going to be looking at it at that level, because it really confuses things when you're looking at conceptual understanding. So we'll be looking at a few things in a slightly abstract way, although all the essential details will be covered. Okay, so what is the TPM, right? Um, Unfortunately, I can't answer this in one sentence. If you've ever heard about this famous story of the six blind men and the elephant, there is an elephant, and the six blind men go and touch various parts of the elephant. One person touches the trunk and then says, "Oh, the elephant is a long tube." Right? Another person touches the elephant's ear and then, says, "Oh, it is like a banana leaf." And another person goes and touches the body and says, "Oh, the elephant is a very rough thing." So each one is telling the truth. I mean, each one is providing their view of the elephant, but nobody is providing the whole truth, right? Like, what does the elephant look like in the whole? And so I'm not going to be able to describe the TPM in the whole, but rather I'm going to be describing the elephant, in this particular case, the TPM, with, as you can see, 6 points of what the TPM is. So the six blind men. Okay. So I'll tell you the TPM and I will sort of describe it uh, in six different ways. So the TPM is a piece of tamper resistant hardware. Okay. And so what does that mean? Right? So by saying tamper resistant hardware, I mean that the TPM is built in such a way that if you try any physical attacks on it, so for example, if you try to read the contents of the registers on the TPM, it's a piece of hardware, it has got registers. If you try to read the registers, by removing the cover of the TPM and performing any electromagnetic attacks or trying to, let's say, solder a wire onto the circuitry over there, it will self-destruct. Okay, so if you try any physical attacks, the chip packaging is in such a way that it will not allow this. Okay, so it's a piece of tamper-resistant hardware. Okay, so the TPM is also a piece of hardware that has its own public-private key pair. Okay, so the private key is hardwired by the manufacturer in the sense that it is set by the manufacturer, cannot be changed, and the corresponding public key is given to you when you purchase the TPM. Okay, so naturally it has to be certified. So if it's manufactured by Intel, you go to the Intel certificate authority and then you can get a certificate for the corresponding key pair. There are other manufacturers also, and you'll have to go to the corresponding certificate authority to get the corresponding digital certificate. So the TPM is not a full-fledged chip, but it is capable of performing some simple computations. In particular, it's capable of performing crypto operations, such as simple RSA encryption and digital signatures, using these keys, of course. All right. So another feature of the TPM is that it's capable of storing a small amount of data securely in on-chip registers. Okay, on-board registers on the TPM itself. So these registers are called platform configuration registers, or PCRs. So modern TPMs have a few tens of these registers, PCR registers. But for the purpose of this lecture, we will just abstract it out and we'll just think about it as one register. Okay. For the purpose of our attestation protocol, it is sufficient to think about it like that. We'll just think about this abstract entity, one register that is storing data in a secure manner. So what does storing it securely mean? So storing it securely means that the data is stored in the register and you cannot change the value of that register except in certain pre-specified ways. Okay. So you cannot just arbitrarily overwrite that register with whatever value you want. Okay. There is a certain pre-specified way of changing the register, which we are getting to. And that's what stores data securely means. And that brings me to the next point. Okay. The TPM supports an API called Tpm Extend. Okay. And this Tpm Extend is supposed to be the only way by which you change the content of the PCR register. So it's called Tpm Extend for a reason. It extends the content of the PCR register with a supplied value. And I will tell you much more about Tpm Extend in the next slide. Okay. Uh, so for now, let us just move on, but understand that TPM Extend is the only way to change the value of the PCR. I'll explain much more detail what extends means. Okay. So finally, I have to tell you some hard truths about the TPM that we are not going to be considering. So I gave you a very simplified view, which is that of a public-private key pair on this TPM and the public-private key pair being used for crypto operations and so on. In reality, it's not like that. In reality, if you look uh, at the specification of the TPM, in fact, there is a complex key hierarchy. Okay, so what's a key hierarchy? So key hierarchy generally means that there is some sort of a root key, which is this public-private key made by the manufacturer. But that key is rarely ever used directly for crypto operations. Rather, you use that root key to derive some other keys, which are called derivative keys. So you see over here, this root key is giving rise to two derivative keys. These derivative keys can give rise to further keys and so on. So you generate this key based on this key. So maybe you hash this with some preset value and you get one key. You hash this with another preset value and you get this and so on. So you get a number of derivative keys, and it is these keys that are used for all crypto operations, never the root key. Okay. So key hierarchy means some sort of a tree structure like this, where there is some root key that's given by the manufacturer and you derive other keys and you use them for your crypto. Why? The reason is because, if there is a brute force attack of some sort and the key by chance gets compromised, you don't want the root key getting compromised, because if the root key gets compromised, the entire hardware is useless. It has to be thrown out and you have to get the new hardware. Whereas if a derivative key gets compromised, no problem. You get another derivative key from the root key and then you can continue your work. Okay, so the root key is actually the manufacturer hardwired key. It's never used directly for encryption and signatures, but we'll pretend for this lecture that there's only one key pair, a public-private key pair, and that is what is used in the attestation protocols. Okay, just to simplify things. But in reality, you should know that there is a complex key hierarchy. All right. So in the next slide, we will start looking at TPM Extend. It's the core of the attestation protocol. So what is this TPM Extend operation? So it is an API that takes two things as inputs. So it takes an input value V. Okay, this input value V is typically a, a value uh, whose bit width is specified. So it's like 20 bits or something like that. Um, I don't know what the latest standard is. Initially, it used to be 20 bits. Sorry, 20 bytes. Uh, but it's a fixed. It's a value of some fixed length. So generally speaking, this V itself is taken as the output of some hash function. Again, that will become clear. So hash function always produces a value of some fixed length, right? SHA-256 produces a 256 byte value. So you can just take that, and that's your input value. Okay, so an input value. So that's the reason why I say it's fixed bit width, is because the V cannot just be like a YouTube movie, okay, or it cannot be an arbitrary string. This V is of some fixed length, okay, 256 bytes, 20 bytes, whatever it is, as specified by the TPM. And the second argument is a PCR register number, okay. So uh, you know, uh, again, we are only going to pretend that there is only one PCR. So you can assume that even this second argument does not exist. Okay. So let's assume that the value of this PCR that is stored in the PCR at any given point in time, let's represent that using cur PCR value, the current value of the PCR. So what does TPM extend do? So TPM extend works like this. It takes the cur PCR value, okay, it concatenates it with V, and it computes a hash. So it could be anything. I mean, it used to be SHA-1. I believe they have upgraded it to SHA-256, but it's a hash function. So for this lecture, we will think about the hash function as SHA-256. Although I believe even this has been upgraded to SHA-512, doesn't really matter. It's a hash function. Okay, you concatenate the PCR value, the current PCR value. You take the input value provided, and you take a SHA hash of this. That result becomes the new PCR value. Okay, so you can see how the PCR value changes in preset ways. You take the old PCR value. The only way to change it is by calling the Tpm extend with V. V gets concatenated with cur-PCR value. A SHA hash is calculated, and the new value, the output of the SHA hash function, becomes the new value of the PCR. Okay, so we are only going to pretend that there's only one PCR register, as I said. So therefore, you can even assume that your API is nothing but Tpm extend with the value that you want to extend the PCR register with. Okay, so if the value that is currently the PCR is, let's say, U, and you call Tpm extend of V, then after the Tpm extend operation, the value in the PCR register becomes SHA-256 of U concatenated with V. All right, let's examine this in more detail. So let's say that the value of the PCR register to start with is 0. Let me ask you what's the value that stored in the register after invoking Tpm extend 3 times, first with argument X, second with argument Y, and third with argument Z. So after step 1, first invocation of Tpm extend, the value will be SHA-256 of 0 concatenated with X. After step 2, it is SHA-256 of this value concatenated with Y. That's what this is. And after step 3, it is SHA-256 of this value concatenated with Z. So you can see it's like a nested hash function. Okay, there's a certain structure that evolves of what value is stored. And this nested structure is also called a hash chain. Okay, so this hash chain has a very interesting property. If you know this value, the first value, or if you know X, Y, and Z, you can calculate the result over here. Okay, or if you know the first output value and you know Y and Z, you can calculate this. At any given point in time, if you know the intermediate value at that particular point in the hash chain, you can calculate the values that come forward in the hash chain. But if you're given, let's say, only step 3, you cannot calculate the value of step 2. You cannot calculate, even if you're given the value of step 3 over here as well as Z, you cannot calculate what value in step 2 got you there. Okay, and the reason is because the hash function is supposed to be hard to invert. Okay, it cannot be reversed easily. Therefore, even if you're given step 3 output and Z, you cannot guess this value easily. Likewise, if you're given the step 1 value and Y, sorry, step 2 value and Y, you cannot calculate the value of step 1. Okay, so it's called a hash chain. And if this sounds very similar to the buzzword du jour, which is blockchain, indeed it is related, right? In a blockchain, you have pretty much exactly the same property that you want to satisfy, which is given any particular block, you won't be able to calculate things that come forward from that block, but never work your way backwards to the old secrets. Okay, so it is very, very closely related to what goes on in a blockchain. That's why it's called hash chain. But the name hash chain actually predates blockchain. All right. So I just took 3 values X, Y, Z here. But remember, these X, Y, Z, I already told you in the previous slide, the values that you give to TPM extend are typically hash values, the values of a hash computation. So maybe X is SHA of V1, Y is SHA of V2, and Z is SHA of V3. then actually what you have after step 3 can be written like this. Shard of this really complex thing over here. It's a whole bunch of shards. Okay. So the thing, as I already told you, is that SHA-256 or any hash function, the property is that it cannot be reversed easily. So if you know the value, if you know the output of the hash function, it's very hard to guess the input that resulted in that hash. Okay, that property is going to be extremely crucial. So of course, you can always guess the value by brute force, but your search space is essentially unbounded with hash functions because hash function takes arbitrary size input and produced a fixed size output. Okay, so given all this machinery, right, how does attestation work? So our setup is going to be the one that we spoke about in the first slide, which is that there's going to be a server and a client. The client is going to challenge the server to prove its claim that it's running some software stack, and the server responds. Okay, the server is going to be called the prover, and the client is going to be called the verifier. So the key thing is that the server must actually run a software stack that is amenable for attestation. In other words, the server software stack must actually interact with the TPM that is installed on the server and perform some TPM extend operations. And that is what is going to be sent to the client, the output from the TPM. So the server is going to be assumed to run this modified software stack. If it's not running, the client will not even talk to that server, right? Because you can't even engage in these attestation protocols with such a server. Okay. So for the purpose of this lecture, we'll be looking at a particular type of attestation, which is also called trusted boot or secure boot. The goal of trusted boot or secure boot is the following. So at boot time, the server is going to give a snapshot of its software stack to the client, and the client is going to be able to verify that the server booted with the software that the server claims it booted with. Okay. So in order to understand this, let us look at how a machine boots. Okay. So when a machine boots, this is what happens. Right? The hardware loads up a piece of software from a fixed location, and that piece of software is called the BIOS or the basic input output system. Okay. So that BIOS then loads up something called a bootloader, which is the screen that you see typically when you start your machine, right? Sometimes if you have a dual boot machine, you can choose which one you want to boot into. That's the bootloader. Then the bootloader loads up the operating system image and then starts, uh, uh, boots the kernel. The kernel in turn starts the applications. Okay. Of course, you, the end user, can interact with the OS and start many more applications, but the OS starts some default applications also. Okay, so the server must declare upfront the versions of all of the software that is part of this boot sequence. All of these versions of the software that the server is declaring go as part of the attestation report, which is this response over here sent from the server to the client. So the reason that we chose this particular simpler version of attestation, which is trusted boot or secure boot, is precisely for the reason that the PCR register of a freshly booted machine always starts at a known value. Okay, in particular 0, right? So when you boot the machine, when it's powered on, every time you power it off and power it on, the PCR value gets reset to 0. So it starts from a deterministic state. So that's why we chose the simple version. Okay. Uh, okay. So this is what happens on the server side. So when the hardware invokes the BIOS, the BIOS has been modified. The hardware actually goes and measures the BIOS, right? These attestation protocols are often also called measurement protocols. It measures the BIOS code. So what does it do? Well, actually what it does is that it goes and computes a SHA-256 hash over the entire region of the code of the BIOS. Okay, the hardware does this. So it says, look, this is the code that I'm going to be executing. Before I execute it, I'll take a SHA-256 hash of all of the code. Okay, and the hardware invokes Tpm Extend of SHA-256 of BIOS, right? Whatever it measured just now of the BIOS, it's going to invoke Tpm Extend with that. So remember, the PCR register starts with a value 0 when the machine is booted. So when the hardware does this operation, the new value of the PCR becomes SHA-256 of 0 extended with the value that it was just extended with, which is SHA-256 of BIOS. So the value that is currently the PCR is SHA-256 of 0 concatenated with SHA-256 of BIOS. Okay, so this is not your regular BIOS. It's a BIOS that is amenable for trusted computing. So it is a slightly modified version of the BIOS that in turn measures the bootloader before invoking it. So before it runs the bootloader, it goes and takes a SHA-256 hash of the bootloader's code and invokes Tpm Extend with that measurement. Okay, and then it'll start the bootloader as usual. So it invokes Tpm Extend with SHA-256 of the bootloader's code. So now what's the value of the PCR? Well, it's SHA-256 of V1, which is this guy over here, concatenated with SHA-256 of the bootloader's code. Now you can guess what happens. The bootloader is also a modified version for trusted computing. It measures the OS code. So it does a SHA-256 over the entire OS image, and it calls TPM extend with that. So the value when the OS is just going to boot in the PCR is SHA-256 of V2 concatenated with SHA-256 of OS. Okay. So we are going to be stopping here, but the operating system in turn measures the applications that it starts. The first three steps are extremely deterministic: the BIOS, the bootloader, and the OS. But after that, applications can start in any order, and it's not really deterministic like the boot process. And so, because it's not deterministic, you need to be able to replay it. And so, the OS actually keeps a measurement log or a measurement list to keep track of the order in which applications are started. I'm not going to be talking about this part over here. It's just a conceptual extension of whatever I'm going to be speaking about for the first three steps. But it is a very important part of real world attestation protocols. In fact, this is what is described in a lot of detail in the assigned reading for uh, today's lecture. So I encourage you to go and see the assigned reading for the details of these measurement lists and how the applications hashes are also stored as part of this measurement list and incorporated as part of the value of the PCR. Okay. So although I'm not going to be discussing this, the details are important, and I am going to be holding you responsible for understanding that by reading the paper. But I'm equipping you in this lecture with all of the machinery to understand that. And that is enough if you understand this. It is in order to understand the paper, it's sufficient to understand the concepts that I'm explaining over here as part of the first three steps. Okay, so we are going to be ignoring applications for now. Okay, and as I said, look at the paper for detail. We'll just focus on this boot process. Okay, so what is the value of the PCR at the end of this boot? Well, it's V3, right? Ignoring this step, just assume that it's V3 for now. So the point is that if the server booted as promised with the software stack that it claims that it booted with. Okay. And if the software stack was not corrupted, either unintentionally because of exploits that found their way into this code, or maliciously because the server is trying to cheat, right? If that was not the case, if the server was in fact honest, then the value of the PCR of the server must be v3, right? If anything was corrupted in this process, the value will not be v3. Why? Well, let's take an example. So let's assume that the operating system was infected, right? And there's some rootkit over there. Then what happens is that when the bootloader measures the OS code, it will also measure the rootkit. And what is measured is not SHA-256 of OS, but SHA-256 of the corrupted OS, which will then, when you take this operation over here, not be equal to v3. v3 is only for the uncorrupted OS. Okay. All right. So what we have done here is that we have built a chain of trust right from the hardware. Okay, so the hardware says that the BIOS SHA is SHA-256 of BIOS. The BIOS says that the bootloader SHA is some value. And the bootloader says that the OS hash is some value. Okay, and you see the final value over here, v3, which is some chain of these hashes computed as shown in the slide over here. Okay, so you're given the final value. You know the original value to start with, which is 0, and you know the values of each one of the steps, and you can therefore recompute the final value yourself by just doing these operations. Okay. The point is that you're trusting every step. You trusted the hardware, and the hardware says that the BIOS SHA is this. And if that BIOS SHA matches what you think should be the correct value of the BIOS, then you have reason to trust the BIOS. And therefore, you will believe everything the BIOS says. The BIOS is saying that the bootloader SHA is this. And if once you verify that the bootloader SHA is what you expect it to be, you can now trust the bootloader. And therefore, you can trust everything the bootloader says. Therefore, you can trust the OS. That is how you build trust in the remote machine. Okay. So the point here is that this chain of trust is all rooted in the hardware. At the end of the day, when you walk down this chain of he said, she said, right, you come down to the hardware. And this hardware is what is trusted, it's tamper proof, and that's why this is called trusted hardware. You trust this, you can build a chain of trust on the remote machine all the way up to the OS and even the applications, and therefore gain trust in the entire machine. But the whole thing comes down to the hardware. That's the TPM in this case. All right. So if the server actually declares its software stack to the client can simulate the boot process of the server and compute the PCR. Okay. So if the server is saying, look, this is the version of the BIOS, this is the version of the bootloader, this is the version of the OS, the client can compute the SHA on their own, and they can actually simulate the boot process of the server, and they will know exactly what value should be there in the server's PCR. Okay, that's the verification step on the client side. Okay, so why can the client do this? Well, it's just a bunch of SHA-256 computations. So you can imagine an attestation protocol going like this, right? The client says, hey, give me your PCR after boot to the server. So the server returns back to the client saying, hey, this is the software configuration I'm running. And hey, by the way, the value in the PCR register is v3. What the client does is that it looks at the software configuration and it says, hey, okay, you're running this particular software. Well, let me go and get the hashes myself from the original sources. Windows, I'll go and ask Microsoft what the hash should be. this particular bootloader, well, I'm going to the corresponding bootloader's uh, website, go download exactly what hash for this particular version, and it can download those hashes from these trusted sources and recompute the hash chain itself, starting from PCR value 0, of course. That's what I mean by simulating the boot. Okay, just do the hashes, just do the equivalent of the TPM extents, and you can compute what is supposed to be in the PCR. And if the client, whatever it computes, matches v3, then yes, the server is in fact running that software. And if not, the server is lying. Okay, or something is wrong in the software stack. Maybe there's malicious software or something like that. Okay, so can anyone see a problem with this protocol? Like, if this is what our protocol is. So the problem is replay. Okay, which is that the server in this particular case, once it knows that v3 is the hash for this software stack, every time the client asks this question, it can just replay this answer. Hey, I'm running the software stack and here's v3. The client looks at the software stack, recomputes the value of the PCR, checks v3, everything matches up, and the server is happily cheating by just replaying this answer over and over. So this is no good. We have to modify it. So how do we protect against replay attacks? Well, if you think back to our lecture on authentication protocols and Needham Schroeder and so on, what was the solution? Well, the solution was nonsense, right? Random numbers. So to prevent replay, the client actually presents a challenge to the server. So it sends, hey, give me your PCR after boot. And hey, by the way, here is my nonce. Here's my challenge. Here's a random number R that I'm giving you. So what the server does is that the server has booted up, obviously, and therefore the value of whatever PCR is there, it's there in the server's TPM. But this R, which was just given by the client, the server is forced to sort of pass it to the TPM. If it doesn't, well, it cannot respond back. But basically, the server passes R to the TPM. And if it doesn't pass R to the TPM, it's not going to get a value. The client will detect that the server is cheating. So if the server wants the client's business, well, it better pass R to the TPM. The TPM is asked to produce a quote of the value in the PCR. So the quote is not just the value of the PCR, but rather a digitally signed version of R concatenated with the value of the PCR. So the TPM, as I said, is capable of doing some simple crypto and digital signatures. So internally within the TPM itself, the server's OS or the software stack is not involved. The TPM hardware itself computes digital signature of R concatenated with PCR. Okay, it's the hardware that's doing this. So what's the digital signature? Well, it's nothing but the RSA encryption with the TPM's private key of R concatenated with PCR. We'll just call that DigSig, okay, digital signature. So now the server responds back to the client with the software stack configuration and the PCR value, which is what we saw in the previous step as well. But the key thing is that the digital signature is also included. The digital signature now contains a response to the particular challenge that the client gave, which is R embedded in this. So now the client can simulate the boot, get the value of the PCR, and also verify the digital signature for a match. Okay, which is all it has to do is that it has to decrypt this digital signature with the TPM's public key and ensure that the corresponding value that has been signed is the R that it gave concatenated with the value of the PCR that it just obtained by doing this simulation of the boot. And if that is the case, well, it also has a freshness guarantee because it knows that the value that it just got, this digital signature, is coming straight from the TPM of the server. So there's no way that the server could have lied or replayed because the response that it just got came straight from the server's TPM, the trusted hardware, in response to a challenge that it just gave. So this is the entire story of attestation protocols. So this is how attestation protocols work. At the end of this process, the client has a freshness guarantee of what's running on the server, and it knows exactly what is running on the server at boot time, of course. So that concludes today's lecture. Uh, Please post your questions on Teams. We will come back to attestation protocols once again when we are looking at SGX and our trust zone, but I will just be mentioning it and moving on, right? I will say that, hey, this is done by attestation. And every time I say that, you should come back to this lecture and understand that this is precisely what is going on. All right. Thank you very much. And that concludes today's lecture.